Okay, so in the previous lecture, we learned about linear and affine functions. So these are functions of several variables that satisfy the property of superposition. I don't know if I mentioned that last time, but basically, I'll just go ahead and write it out. So last time, well, before I write that, I have to write the title of today's lecture. This is called regression model. Okay, so just recall, first bit is a linear function of several n variables, means that f of alpha times x plus beta times y is equal to alpha times f of x plus beta times f of y. And then also that an affine function equals a linear function plus a constant. Okay, and one such example for an affine function that we considered, one of these functions has the form the inner product plus a constant. Now, for the purposes of this recording, I'm going to change up the notation a little bit and say that, let's write it out. Y hat equals to x times beta plus v is called a regression model. Okay. Now your input here is x, but what is beta? What is v? So beta is just some n vector. Okay. And these are called the weights or coefficients, as I mentioned last time. V here is a scalar, just some number. Okay. X is your feature vector. Also known as your regressors. Again, that equation right there. And it's also, this is like your input to the function. What you input into the model. Think of y hat as your, this whole equation is your model. Your input are your features or your regressors. You have your weights, you have a scalar. And finally, y hat is the prediction for well, prediction slash label for the input x, or the features x. Okay. Now, y hat approximates y, which is the true value, which is the true label for the input x. Okay. Now, what is this model doing? Why is it called a model? What are the features? What is this thing? Well, as I just erased here a moment ago, we can say gather data about houses, for example. So a company can gather data, and what does this data look like? It can look like location, 1, price, 1, dot, location, M or something. I'll use capital N, price, capital N. So we go out and we collect a bunch of data about houses, and there may be coordinates or some type of way of numbering their location, some numerical value. And for each of those areas, we have a price of a house. And suppose that there is an area that isn't in our list that is starting to build close to things in our list, and we would like to predict the price of housing in that area that isn't in our data. We can use our data to get a rough estimate of that. So for example, if your x-axis here is the location and your y-axis is your price, we can plot this data to get a sense of what's happening here. And maybe the data that we have, that we collect, looks something like this. And we want to use this data to predict on something that isn't in there. Well, how can we do that? Well, one way that we can do that is to use this data and to find an affine function that approximates the data. So for example, this could be our function y hat. We find an affine function that approximates that data. And then when we do that and we plug in, so this is like the coordinates of like the new neighborhood. We want to predict the houses, the price of the houses in that neighborhood. We put those coordinates into the function, and we get out the predicted price. So finding that line gives us a price, and then we can kind of more or less guess around that price with some confidence, put a confidence interval around that price, and we have a reasonable, we would hope to have a reasonable estimate on the price of houses that are being built in that new area. Okay, now let's go ahead and program this. Well, before we do that, I should probably make note of a few things that your textbook doesn't mention. So finding this line, okay, this line, this regression model what are the things that we need to find in order to fit that model? Well, so to find the best affine approximation to the data, i.e., solve the regression model. So to find the best affine approximation to the data, the only things that we have access to are b and b, right? Our coefficient vector and our scalar there. This is a variable, that's going to change. The only thing we have access to are b and b. So we need to find the optimal b, which is just some n-dimensional vector, and v, which is just some scalar. Finding this line, using the data to find that line, is called linear regression. No. It's not called linear regression to find this line because there are many ways to find this line. There are many different ways to do that. One way to do this is with linear regression. Is to use linear regression. There's many ways to do that. One way, linear regression. This is, so linear regression, and linear regression can be solved a bunch of different ways too. It's just like it gets more and more specific, but linear regression in general is considered supervised learning. A subfield of machine learning. So the general goal in supervised learning is to use data feature vectors together with the known output, the known label, use that to build a model that will be able to make predictions on data that you do not have. Okay. And doing this to solve the regression model is just one instance of it. Solving the regression model with linear regression is one instance of that. And I'm going to show you how to do this using sklearn in Python. It's simple to use to import import packages to solve this model. Okay. So I'm going to go ahead and share my screen. Okay. So now, one moment here. 1 second. Give me 1 second. While I'm doing this, go to Blackboard. You'll see a data set folder. Inside that data set, I put a data set for housing that you can download, and that's the data set that I'll be using. Okay. All right, so let me share my screen. All right, so if you go to Blackboard and you open up, where is it? Course content, data sets, housing data. You can download this CSV file and stick it in a folder that you're going to want to navigate to once you open Anaconda. So if you go to Anaconda, you open up a Jupyter notebook. Okay. So I know that I saved that in my teaching datasets folder. Okay, so now I'm gonna do new Python. Okay, so I'm not sure how familiar all of you are with Python. I'm just gonna go ahead and do this as if I was doing it on my own, and you can watch this video on YouTube and kind of copy me. But just know that in my current directory, I have that housing data right here, okay? So once I saw that I have the housing data in this directory, I just made a new Jupyter notebook. Okay, so what am I gonna use? So I'm gonna use matplot library.pyplot. I'm gonna import that as BLT. I'm going to import pandas as PD. I'm going to import NumPy as NP, and I'm going to import sklearn. Not going to import everything. From sklearn, I'm going to import the linear model. Okay, so now that I've done that, I'm going to read my data in. So I'm going to say data is equal to.
Do we have to download, oh, excuse me. Do we have to download that sklearn package?
If you imported, if you downloaded Anaconda, I think it would have installed.
Awesome. I haven't typed it because I don't have Jupyter notebooks on this one.
Okay. If it isn't, then you can just, I think it's like, if it's not, you can do that in the Jupyter notebook and it will install it for you. Just do it above all the import statements. Okay, so I'm going to say data is equal to pd.read CSV. What was the name that I gave it? It was housing 2, I think, .csv. So, all right. So there's my CSV file. Now we have price, area, bedrooms, bathrooms, story. I'm going to go ahead and use as my feature vectors. I'm going to use the area and the bedrooms. Okay. And I'm going to use only the first 500 rows. I want to leave out some rows to test how good my model is. So to do that, I'm going to do this in a few steps. I'm going to say x is equal to np.array. Hold on. So I'm going to make a list of NumPy arrays, and I'm say little x0. Hold on. So put this in a list. Little x1. Close that list. For x in zip data dot, what did I say? Area and bedrooms. So area up to 500 and data dot bedrooms up to 500. Okay, and now zip is just going to make tuples of entries in area and entries in bedroom. So each X in that zip, the 0 entry comes from the area, the 1 entry comes to the bedroom. I'm taking those numbers, I'm sticking them inside of a list, and then I'm making those into NumPy arrays, which you can think of them as vectors, and I'm putting those in a list. And again, I'm not expecting you to know all of these things right now. I'm just showing you how we can apply these linear models or this regression model. Okay, so these are my feature vectors. They're all inside of there. Okay, so for example, like if I look at X, these are vectors. This entry is the area. This is the number of bedrooms. Okay, so now I'm going to get my labels for the first 500 entries. And I noticed real quick, I noticed that these prices are really large. So I'm just going to divide that by 1,000 to make them smaller because it'll be easier to plot later. So what I'll do is I'll say y divided by 1,000 for y in data dot price up to
I have one quick question. What is that zip function doing before? Yeah, the
right
zip
here.
function.
The zip
Yes,
function, the zip function makes tuples. So I'll show you after I make my y. So I'm putting inside capital Y the prices up to 500, and I'm dividing them by 1,000 just to make them smaller. And I'll just keep track of that later. Okay, so real fast to understand what zip is. So like, let me just, so if A is equal to 1, 2, 3, and B is equal to A, B, C, then I can make a new list. I'll call it L equal to X for X in zip A comma B. And then I'm going to print L. I can just type L. So see how it matched them up? One went with A, 2 went with B, 3 went with C. See that?
yes, sir.
So it takes entries in A and B and it matches them up into little tuples. So what am I doing here? I am, if I wanted to, instead of have tuples, I wanted to have lists. I could do x0 comma x1, put that in a list. And now now L is all these lists now. So that's what I did to X, except for I took those lists and I turned them into NumPy arrays, which are like vectors. Okay. So now, yeah, I have, let me just get rid of this cell now here. So I have my feature vectors, I have my Ys, and I'm going to solve the regression model. Okay. So sklearn has a way of doing this. So I'm going to say reg is equal to linear model dot linear regression. So it's an empty model. And again, you don't necessarily need to understand everything about sklearn. I'm just showing you the application right now. So I made an empty model here. And now I'm going to ask that model to fit. So reg.fit, and I'm going to fit it on my X with my Y. Okay. Now those two lines of code solves the problem. It solves linear regression for these features and these labels. Okay. Now, when you solve the model, you'll get coefficients. You'll get your coefficient beta. So if you look at your notes from today's lecture, beta is the coefficient vector or the weight vector that multiplies your input x. So you can look at those by doing reg dot coefficient underscore. And there is your vector of coefficients. That's your weight vector. And if you want to know your bias or your intercept, you can do reg dot intercept with an underscore. Okay. So now what do I want to do? I want to see how well my model is performing on data that it didn't learn on, right? I fit this model on these pieces of data, and now I'm going to test it. And to test it, I'm going to say x underscore test. So I'm going to come up here and just copy this. But now, instead of ending at 500, I'm going to start there. Okay. So these are all the data that we didn't use to fit this model. And then here, I'm going to make a y test. And now I'm going to look at all the ones that we didn't use. So these all should match up. Okay. So 500 to the end. And then I'm going to say y hat. So my predictions, I'm going to put into here. And I can do that by saying x, the at symbol. So this is x inner product reg dot coefficient vector. So this is the coefficient vector times x. This at symbol is the numpy inner product symbol. And then I'm going to add reg dot intercept underscore for x in x test. Okay.
So that dot fit, the dot coefficient, and the dot intercept are all a part of the sklearn?
Yes. Yeah. So sklearn has a model type, and that's what I assigned up here. It's this model called linear regression, and these models have fit methods and coefficient methods, intercepts, or those are attributes. And to access them after you fit your model, that's how you get them. So this, you can really read this if you look at your notes, x inner product beta plus v. So these are our predictions on the data that we didn't use to fit.
So what is that coefficient and intercept? What are those actually? Like what are the numbers adding up to the summations that we calculated before?
Yes, so you see this right here?
Mm-hmm.
This is like, it's gonna look like this. It's gonna be like 3.7 whatever times x1 plus 7.06 times x2 plus our bias, which is 855.4 something.
So the coefficients are like a scalar towards the vector, and then the intercept is just the constant that we added, the plus b?
Yes.
Okay.
Yes. And that's why we take the dot product here to do this times the first entry plus this times the second entry, and then I'm adding the intercept at the end. This is our prediction for each of those x's in x test.
So the fit is the product.
No, the reg.fit, that's solved it. It found the coefficients and it found the intercept. It found the best coefficients possible and the best intercept possible.
Okay, you just printed them out below, right? Like with the other code down there?
Yeah.
Okay, awesome.
So now I have the true values for my testing data and the predicted values, right? Maybe I'll even write that. Right, predict. Okay. Okay, so shift enter. So now I can see how well I did. So PLT dot plot. So I'm going to plot y test versus y test. Now this is the line that is the true data fit. You'll see what I'm talking about after I plot it. I'll say line style equal dashed, color equal red. And now I'm going to scatter the true so y test versus y predict. I'm going to see how many times those overlap with each other.
What is the y test by y test? Why would we put that in twice?
You'll see in a second when I plot it. What do I want to do? I was going to do something. Oh, marker. And then color equal blue. I'll say PLT dot X label. This will be, what is this? This is going to be true price in thousands of dollars, because we divided by 1,000 earlier. And then on the x-axis, I mean on the y-axis, we'll have predicted price. Okay, and let's look at what this does. Oh, that's not good, right? That line doesn't look like it's fitting our data at all. So that's actually a good point to make here, is that when you're inputting your data, your input data can mess with things. So what I'm going to do for now, just to illustrate what this line is doing better, what I'm going to do for now is I'm going to I'm going to train on, let's try this again. Okay.
So, oh, give me 1 second. So did you basically take a sample size of the first 500 and then kind of test them to see if the rest of the data set was equal or was like fitted to that line?
Yeah, so the whole goal was to use training data to make a model that can make predictions on data it hasn't seen. So I left out the last bit of data to test on. So maybe, let me try to go a little bit higher here. 540, 540, 540. So you gotta run that again, fit again. And then now let's look at 540 to the end. One last time. Really what I should do is I should shuffle the data around, but I don't want to get into details of that because we're not. Where is it? Hey, I'm just going to train on the whole thing. So I'm just going to train on the whole thing. This is not what you would do in practice, but I just want to illustrate what's happening here. So there. Okay, so now I'm just going to plot the whole thing. I can just use y now because there is no test set. And then y versus y predict. Yep. Something. Oh, this should be in X. Okay, so this illustrates the point. I was trying to do it the truly correct way, but I didn't shuffle the data ahead of time, so there was something going on with that. But now here, look. So this red line here, your true price is 40,000, and see how I did Y twice? The true price was 40, and then on that red line is 40. You see that? So if your true price is this axis, the predicted price should be on this line here. But it's not. And that's because we're predicting for like this house right here, it has a true price of 60,000, but we predicted like 90,000. This house right here. See how it's far away? But all of these houses here, we are close to the red line, which means that our prediction is close to the true value. So we're a little bit above here, we're a little bit below here, but we're kind of good, right? So our predictions are pretty, like, for example, all the houses here, we predicted the exact correct price. Okay. So now if we took in more data, we would presumably be okay. All right. And that's all I wanted to illustrate. I just that we found an affine function that approximates this data. This is the affine function we found. We found the coefficients and the intercept by, well, we didn't find it. This built-in fit method for linear regression found it, but we will learn linear regression this semester. Okay. All right. So I'm going to go ahead and stop the recording there.
I have like 2 random questions.